Greetings, everybody. So we are continuing our video showing how to solve differential equations. And on the previous videos, we covered the first two cases, okay, having real poles with multiplicity 1 and real poles with a higher multiplicity. So what happens when eventually we are going to get a polynomial with complex poles, right? So I've written them down right here. So what is the process when the poles are complex? Okay. The process remains the same. Okay, we are going to continue by breaking down this function, this rational function, into partial fractions. Okay, now, first of all, we are computing the coefficients on the top in the same way as before. But these coefficients now just happen to be complex conjugate with each other. So I don't have to compute both of them, I just need to compute one of them. So then what are we going to do? If we are doing an inverse Laplace transform, okay, which is absolutely correct, we are going to end up with this sort of terms, you know, z of t u to t minus z of t u to t. Okay, I'm sorry, plus z bar of u. Okay, but here, remember I told you that this pole is a complex pole. So this will give us a complex function, right? Which is a bit baffling first, because, you know, let's say this differential equation is used to, you know, represent the solution of a mechanical system. So x represents, for example, displacement or velocity or acceleration. Okay, what the hell? Does that mean that the displacement is a complex function? This makes no sense in the real world, right? We don't have, you know, complex displacement. So are we doing something wrong? No, absolutely not. You are not doing something wrong. And obviously the displacement is not a complex function. Okay. So these two individual functions themselves are complex, but when combined together, there is a very, you know, relatively simple process where we combine these two solutions and simplify them, and using some very basic algebra and calculus, what we are going to end up is, of course, a real function. Okay. So obviously the displacement is not a complex function, it is a real one. Okay. So these two terms are combined together into a single term in the solution. And this is the solution right here. We have 2 times. Here we have absolute value of k, and this is a complex number. So we are referring to a complex magnitude of, to a magnitude of the complex number. And then for this pole, the real part is going to end up, as with the previous cases, into the exponential function. Okay. The complex part, the imaginary part, is going to end up as the coefficient of the cosine function. Okay. And then we have theta, and theta represents, let's say, we have kappa here. So theta is the angle of this complex number right here. Okay, so this is theta. But the idea is that we consider theta for the coefficient that corresponds to this pole right here that has a positive imaginary part. Okay, so we're going to see which is this pole, and we're going to take the coefficient that corresponds to this pole exactly. Okay, so that's it. The process is very simple. It looks complex, but actually it isn't. And for that matter, I'm going to show you a couple of examples just to get acquainted with the whole process. Okay, so let's go here and let's start with our first example. I'm giving you a transfer function, which is, let me see, this plus 8. All right, and for this, I'm searching for the impulse response. Okay. Great, so let's begin by solving this system. So the output is the transfer function multiplied by the Laplace of the input. So here, of course, we have the impulse function, so the Laplace is equal to 1. So we're going to end up with 1 over s squared plus 4s plus 8. So we need to break this down into individual fractions. So let's compute the root. The root is this. Okay, 16 minus 4 times 8 minus 32, it's minus 16. So the roots are minus 4 plus minus 4i, since we have a negative value here, over 4, which is equal to minus 2 plus minus 2 times I. Great, 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 great. So this will give us this fraction right here, s plus 2 plus 2i plus beta over s plus 2 minus 2i. And remember, these are complex conjugates. So I don't need to compute both A and B. I just need to compute one of them. So let's compute A, the same way as before. So this is the limit, pretty much like with what we did with the previous cases. S goes to minus 2 minus 2i, all right, of s plus 2 plus 2i of 1 over, I'm going to write this in a factored form, multiplied by s plus 2 minus 2. This is equal to this. We have 1 over minus 2 times I plus 2 minus 2 times I. This gets cancelled out, and we have 1 over minus 4i. And of course, I'm not going to leave this as it is. I'm going to multiply this fraction. So this is going to give us yi over 4. Nice. Very nice. And this is pretty much what we need. Okay, so the root here, which was minus 2 minus 2i, has a coefficient equal to I over 4. And the root, which is minus 2 plus 2i, has a coefficient that is equal to minus I over 4, because these two are complex conjugate. Great. So for the solution, I'm going to need the angle of one of the two coefficients. But as I told you, we are gonna go with the angle of the coefficient that corresponds with this root that has a positive imaginary part. So beta, let me write this down, beta is minus I over 4. So the angle here is this one. So angle of beta is, of course, 270 degrees. Okay, so that's about it. We only need one more thing. We only need also, of course, the magnitude. In this case, the magnitude of both, of course. These values is the same. And in this case, it is 1 over 4. Right, very easy to remember the magnitude of a complex number. So let's write down our solution finally. Let's put an asterisk here. And the solution gets computed this way. And I'm going to go down a little bit more. Okay. So the solution, since we don't have any other terms, is this 2 times this term right here, multiplied by epsilon to the, this is the root, so this is the real part, minus 2, so it's minus 2 of t multiplied by the cosine of, this is the factor here, we have 2 times t plus 270 degrees, which is this factor right here. Okay, so this is 2 times 1 over 4, okay, epsilon to the minus 2 of t multiplied by cosine 2 of t plus 270. And this is it. Congratulations. We just solved a differential equation for the impulse response that had, also complex roots. And it is very easy to compute this solution because what do we have here? We have an oscillating term. At time 0, this is going to give us the cosine of 270. So it's going to start from 0. Naturally, since we are talking about impulse response. And what is this? This is a cosine term that oscillates multiplied by an exponential term that goes to 0. So this will give us an oscillation that will slowly, slowly, slowly thin out and go to 0. Okay, so simply put, I'm expecting an oscillation just like that. Okay, so that's it. Okay, this is the whole process, finding out the root for the case of complex zeros. Okay, finding out the solution, I'm sorry, for the case of complex roots. So let's give another example, a little bit larger, for the step response this time. So let's clean everything. And now let's see. I'm going to give you a differential equation. Okay, I'm going to give you this transfer function. I say differential equation obviously because they are equivalent, right? So s squared plus 2 of s plus 2. And this time I'm searching the step response. So let's begin by solving the system. We have the output being transfer function multiplied by the input. So we have 1 over s multiplied by s squared plus 2s plus 2. Now let's find these roots. So we have d is equal to 4 minus yes, minus 8, sorry. So it's minus 4. And then the roots are minus 2 plus minus 2 times I over 2. So the roots are minus 1 plus minus I. So this will get broken down into 3 fractions. So beta over s plus 1 plus, oops, I'm sorry, plus I, and c of s plus 1 minus I. And now our job is to find the 3 coefficients. So alpha, of course, is very easy. It is the limit as s goes to 0 of s multiplied by this whole thing. And this gives us 1 over 2. Nice. And then we only need to compute one of the two coefficients. It's the limit as s goes to minus 1 minus I of s plus 1 plus I multiplied by 1 over s by s plus 1 minus I. Okay, so this requires a couple of operations. Okay, so it is going to be a bit tiring, but nothing extreme. Minus 1 minus I multiplied by minus 1 minus I plus 1 minus I. So we have 1 over minus 1 minus I multiplied by minus 2 times I. So shoot this. So this is the only part that I consider to be a little bit tiring, but of course you can use a computer for that. We have 2 times I minus 2 times, no, plus, I'm sorry, 2 times I squared. So this is going to be 1 over minus 2 plus 2I. And I'm not going to leave it like that. I'm going to multiply numerator and denominator by the complex conjugate, which will give us minus 2 minus 2I over 2 squared plus 2 squared. So this is going to be minus 1 over 8 minus 1 over 8I. Not 1 over 8, sorry, because this is 2 and 2, and this is a 4, so this is going to be, I'm sorry, 1 over 4. Okay, so this is it. We found that, and now we only need to find the corresponding angle. So let's see. One of these roots, which is minus 1 minus I, has this coefficient beta, which is minus 1 over 4 minus 1 over 4i. And the other pole, which is minus 1 plus I, has this coefficient c, which is minus 1 over 4, I'm sorry, plus over 4i. So which of these are we going to take for the angle? We're going to take c because this corresponds to the positive uh, part of the roots. So let's see. Of course, for both of these, their magnitude is the same. We have 1 over 16 plus 1 over 16, which gives us 2 over 16. So we have the root of 1 over 8. So we have the root of 2 sqrt of 2. Angle we have minus 1/4 plus 1/4. So we are here. So this is C, and this is the angle. Okay, so this angle here is obviously 90 degrees plus 45 degrees. So it's 135 degrees. So this is it. We have practically almost solved our system. So let's go a little bit below. And then by considering the Laplace transform, the inverse Laplace transform for the out y of s, we obtain this thing. We've done 1 over 2 u of t. And this is because, of course, we have three terms, as you see, and one of them corresponds to a step input, and the coefficient is 1 over 2. The other two terms, we are going to combine them together into a single formula, which let's write it down right here. So it is plus 2 times this number right here, which is 1 over 2 sqrt of 2, nice, multiplied by the exponential of minus t, okay, multiplied by the cosine of, this is the coefficient, which is 1, so it's t plus 135 degrees. Right, amazing. So this step response, I'm sorry, is going to be like that. We have two terms, and let's remember, one of them is a fixed value, so this will not go anywhere. Okay, and this is an exponential multiplied by a cosine. So this term is an oscillating term that steadily goes to zero. So in this case, the system again will obtain an oscillation of a kind, and it will eventually settle into this position, 1.5. Okay. So it's relatively easy to solve systems that have complex poles, right? It's not extremely difficult. I mean, it is a bit tiring to compute the coefficients, but that's it. Other than that, the process is very, very simple. The most basic thing to remember is this. When the poles of the transfer function, okay, are complex, we are going to have oscillations. Okay, this is the most important information. Complex poles result in oscillations. Okay, so this is what you should remember absolutely. And of course, if you remember correctly, I told you that there are overall 4 cases for the behavior. So remember, you may have something like complex poles, okay, and you may have them with multiplicity as well. So what does this give us? In the simpler case, we are going to have exponential terms, right, multiplied by the input. If we have, multiplicities, we are going to end up with all of these additional terms, right? And more and more and more depending on the multiplicity, of course. Okay, so for each additional multiplicity, you get t times the exponential, t squared times the exponential, and so on and so on. And the same thing happens when you have complex conjugate poles. Okay, so when you have something like that, in the simpler case, you are going to end up with an exponential multiplied by cosine. Okay, doesn't matter what it is inside. But in all other cases where you also have multiplicity, which is very, very unlikely to happen, what you're gonna end up is with having additional terms, just like that. So similarly to before, you're going to end up with the exponential multiplied by the cosine, but also multiplied by some t and maybe some t squared of the exponential. So the idea is exactly the same, but we don't usually solve these kind of exercises because they end up being extremely tiring to solve and find the coefficients. But these are all the four cases. Poles with multiplicity 1, poles with higher multiplicity, complex poles, and complex poles with multiplicity. Okay, so now you have all the information you need to solve any form of differential equation. So even if the differential equation is of 100th order, I mean, you're gonna have to spend some time finding the coefficients, but the process is the same. You break down the fraction into individual partial fractions, compute the coefficients, and then take the inverse Laplace transform. Okay, simple as that. So any question that you have, write them down in the comments below, and I'll see you in the next video.